When a giant rainforest mantis spots a target, it fully unfolds its spiky raptorial legs and makes contact in a fraction of a second. Filmed at high speed, we can see that this entire predatory strike lasts exactly 50 to 100 milliseconds. For biological context, a standard human eye blink takes about 300 milliseconds. The insect executes a targeted physical hunting maneuver in 1/3 the time it takes you to simply twitch an eyelid. At this scale, the time required for any neural feedback loop is longer than the action itself, meaning the insect must commit to the movement's entire trajectory before its legs ever leave its body. In most animals, voluntary movement relies on a closed-loop neural system. Sensory organs collect data, send it to the brain for processing, and wait for a command. Information enters the eye, travels to the brain, the processor calculates a response, and transmits a motor command back to the limb. Pushing this signal across that distance adds a mandatory delay. By the time the instruction arrives, the fast-moving prey has already escaped. In extreme high-speed predation, central intelligence and brain processing become physical liabilities. To solve this latency problem, the mantis routes its attack commands around the brain entirely. The insect relies on a decentralized network of nerve clusters, specifically the prothoracic ganglion located in its thorax. The specific motor neurons that control the major leg nerve, designated N4, physically reside directly inside this thoracic hub. While vertebrates rely on the brain to pilot their limbs, the mantis thorax acts as a semi-autonomous center, governing its own body sector. The insect reduces signal delay by moving the command center directly to the point of impact, right next to the physical weapons. In 1963, physiologist Kenneth D. Roeder discovered that the mantis brain does not actually drive the attack. Through descending inhibition, the head constantly broadcasts a downward signal suppressing movement. The strike is a preloaded motor program in the thoracic ganglion, held back like a compressed spring. Upon spotting prey, the brain cuts this inhibition, and the thoracic node instantly discharges the attack. This is an open-loop execution. Once the strike begins, it is a purely ballistic motion. The mantis cannot correct its aim mid-flight. High-speed predatory behavior is achieved when the brain acts solely as a safety switch, relinquishing real-time control to local hardware. This anatomical shortcut explains the speed, but tests show that adult female mantises hit with an impact force of roughly 196 millinewtons. In biological systems, the force of a strike typically scales in proportion to the two-dimensional cross-sectional area of the muscle. This scatter plot shows how animal strike force correlates with muscle size. The data point for the adult female mantis sits far above the limit predicted by her muscular cross-section. To explain this anomaly, entomologists suspect the mantis utilizes a localized latch-and-spring mechanism within the leg joint. Instead of relying on instant muscular contraction, a latch-and-spring system builds up mechanical energy slowly and releases it all at once. The mantis offloads both its processing and its kinetic energy generation away from central biological systems. When engineers build traditional autonomous robots, the hardware often stutters over uneven terrain. The machine suffers from a CPU bottleneck. A single processor is attempting to plan every micro-movement for every mechanical joint simultaneously. This mirrors the exact latency problem found in biological closed-loop nervous systems. Attempting to solve every physical interaction through a centralized processor creates an unavoidable delay in machine response. To bypass these limitations, researchers developed an engineering framework called MantisBot. Engineers translated the mantis's thoracic ganglia into code using conductance-based neural simulations. This moves the processing power to the edge of the network, housing the compute algorithms inside the robotic joints themselves. Like the mantis thorax, these robotic joints operate semi-autonomously, executing motor programs without ever routing data back to the central CPU. The central CPU is relegated to the role of the brain, acting only as an inhibitor or safety switch rather than a driver. From biological evolution to autonomous machines, the solution to the latency bottleneck remains the same: offloading calculation to the point of impact. Dive deeper into the hidden secrets that shape our reality. Click the subscribe button, activate the bell, and see you in the next scientific investigation, only on TEMBODocs.